Chapter is Magnetic Field, A2 chapter, and for the paper 4. Definition of the magnetic field is area of the region around a magnet or around current carrying conductor in which a moving charged particle can experience force is called magnetic field. Area of the region around a magnet or current carrying conductor mean wire in which a moving charged particle can experience force. Now, magnetic field is represented by lines. Suppose we have two fields. Number one is this, and suppose number two is this. There is one similarity. This field is uniform because the lines are straight, parallel to each other. This is also uniform, but the difference is this field is weak and this number two field is strong. So if lines are parallel, then the field is uniform and the spacing between the two lines represents the strength. Smaller the spacing, stronger the field. And number three, if the lines are not straight, they are curved, then this is non-uniform magnetic field. And the number four, this is non-uniform, but the gaps are smaller than the previous. So this is non-uniform, but strong. This is non-uniform weak, and this is non-uniform strong. Now next, there is a physical quantity which is called magnetic flux. It is represented by phi. It is scalar physical quantity and measured in Weber, capital W with small b. And it is actually the number of magnetic field lines passing through certain area. So the number of the magnetic field lines passing through certain area describes the magnetic flux. So this magnetic flux phi, it depends on number one, strength of the magnetic field, which is represented by capital B, and it's a vector quantity and measured in Tesla. So the magnetic flux proportional to magnetic field strength. And number two, it depends on the area, the size of the area, and the area is scalar. It is measured in meter square. And the number third is very, very important, is actually the angle theta between magnetic field lines and plane of area. Suppose field lines are directed in this direction and the plane of the area is perpendicular to it. Look, this is perpendicular. So the angle theta is 90. So the flux in this case will be maximum. But if the field lines are horizontal and the plane of the area is also horizontal, look, same, parallel, angle theta 0. So the flux is a minimum mean 0. So this magnetic flux, which is phi, depends on three factors: strength of the magnetic field, area, and number three, the angle, and angle theta. Theta 90, so it's maximum. So sine 90 maximum value, so 1. So it depends on B, it depends on area, and number three, it depends on the sine value, sine of the angle. So we can write the formula for this phi: magnetic field strength multiplied by area multiplied by sine theta. So phi is equal to then BA sine theta. This B is measured in Tesla. This is magnetic field strength, like electric field strength, gravitational field strength. It's a vector. A is the area, and theta is the angle between magnetic field line and the plane of the area. If the angle is kept always 90 degree, so the phi value maximum will be BA. And this B, which is magnetic field strength, can be written as phi divided by A. Phi is scalar, it is measured in Weber. Area scalar, measured in meter square. But the B is vector, it is measured in Tesla. And due to this formula, this B, which is actually magnetic field strength, represented by B, can also be written as, known as magnetic flux density, because it is equal to flux divided by area. So the magnetic field strength is also called magnetic flux density. So there is no difference between magnetic field strength B and the magnetic flux density. This magnetic field strength in our A-level syllabus is required in three different situations. Number one, suppose we have an infinity long conductor carrying some current, and according to right hand grip rule, this is the direction of the magnetic field around it, and gradually the field is decreasing. So we have to increase the gap between two circles. So this wire is carrying current I, and we have to measure the strength of the magnetic field at any point around it. Suppose this is the point P. So the first of all, look at the current, it is I, and then measure the perpendicular distance of the point from the wire, so D. Then the B at point P in this situation is directly proportional to current, and number two, B at P is inversely proportional to D. So directly proportional to current, but inversely proportional to D. When these two relations are joined together, so the B at P is current divided by distance, and the constant B is equal to mu naught divided by 2 pi I divided by D. So this is the constant here, and this mu naught is called permeability of the free space. and free space mean the vacuum. Permeability of the free space, and its value will be given, mu naught will be given 4 pi into 10 power minus 7 with its unit. So this is the value of the constant. So magnetic field strength B around a current carrying conductor, around a current carrying wire at any point is mu naught I divided by 2 pi d. So this is the first requirement. Now, number two, if we have a coil, this is the coil like solenoid. When current is supplied to it, if the current flowing in this direction in clockwise, so this is south pole, this is north pole of the electromagnet, and the magnetic field lines are like this. Now, the stronger magnetic field is exactly at the middle of the coil, not at the poles, because the strength depends on the gap between two lines. The gap between two lines, smallest will be exactly at the middle. So at this point, the magnetic field strength depends on current. Number two, it depends on the number of turns of the coil. And number three, it depends on the length of the wire, length of the coil. This effective length from one end to the other end. So when we will combine B directly proportional to Ni over L, again, B is equal to mu naught Ni over L, and this N over L is called number of turns per unit length. Number has no unit, length has meter, so this N over L is represented by small n, and with unit, meter power minus 1. So sometimes this formula will be written mu naught Ni. So small n mean number of turns divided by the length of the coil. So mu naught is the permeability. This is the number of turns per unit length, and this I current supplied to the coil, to the solenoid. And the number three, suppose we have a flat circular coil. And the current is supplied to it I. This is the center where all field lines are passing. Look, all are gathering here. So this is a stronger magnetic field area. So the magnetic field strength at this point, the center, directly proportional to the current, directly proportional to the number of turns, but it is inversely proportional to diameter. So when we will combine, it becomes B directly proportional to Ni over diameter. So B is equal to mu naught Ni over diameter, but d distance, d diameter, to avoid the confusion, mu naught Ni and this diameter d can be written as 2 times radius. So this is the formula for the B exactly at the center of the flat circular coil. And this is mu naught Ni for a solenoid exactly at the center. And this first for the wire, and any point around the wire, B is equal to mu naught Ni over 2 pi d. Now, according to our previous knowledge, O-level, when a current carrying wire is placed inside the magnetic field wire, I mean, it experiences force. And the direction of the force can be determined by Fleming left-hand rule. So when a current carrying wire is placed inside the magnetic field, wire experiences force, and the direction of the force is determined by Fleming left-hand rule. So look, this is the direction of the magnetic field. This is uniform magnetic field. It is represented by B and unit Tesla. Now this wire is placed inside this magnetic field, and suppose this is the direction of the current. Now, according to Fleming left-hand rule, then the force is into the page, according to Fleming left-hand rule. But when magnetic field is same, this is the wire, and the current is downward, then according to Fleming left-hand rule, the now force is out of the page. So this is our knowledge from the O-level. Now, the size of the force. Yes, we can determine the direction of the force by the Fleming, but this magnetic force, FB, it depends on, number one, what is the strength of the magnetic field B? Which is now called the magnetic flux density. So the force and B both are directly proportional. And number two, it depends on the current I. So larger the current, greater the force, so both are directly proportional. And number three, the length of wire inside the magnetic field, not the whole length, inside the magnetic field, mean the only length which is inside. So this is the length, this one, not hold the whole wire. So F directly proportional to L. And number four, it also depends on the angle between the current and the magnetic field. And in O-level we have done, if the angle is 90 degree, then the force is maximum. If the angle is 0, then the force is 0. It means if the wire is placed parallel to the magnetic field, no force is experienced, right? But when perpendicular, so force is maximum, and the perpendicular mean the angle theta 90, so sine theta maximum, 90 maximum. So F directly proportional to the value of sine theta. So whenever the graph is plotted between force and these physical quantities, suppose this is 0, this is B in Tesla, our current in ampere, length in meter, our sine theta, and sine theta no unit because it's not a physical quantity, it's a number. Then force is directly proportional to all four, so straight line passing through the origin. But for each value, B, I, L, sine theta, the gradient will be different. But the shape of the graph will remain same because F is directly proportional to B, directly proportional to I, directly proportional to L, directly proportional to sine theta. But if the graph is required between angle theta and the force in Newton, then this is not a straight line because it depends on the sign. So there will be a sine graph. Zero, 90 degree, 180 degree, 270 degree, and 360. So sine graph because it depends on the sine theta. Now, 4 factors are affecting this. One is the B, magnetic field strength, magnetic flux density. Other is the current. Next is the length, and then the angle with sine theta. So the formula for the force will be BIL sine theta. B is the magnetic flux density, I is the current, L is the length, and sine theta is the ratio of the angle. So this is the important formula. Force magnetic is equal to BIL sine theta. When it is confirmed that theta is 90 degree, then we can write F is equal to just BIL because sine 90 is 1. Now this formula can be written as B is equal to F over IL sine theta. So if the current value is 1 ampere, length is also 1 meter, and the sine theta value is 1, mean the wire is placed perpendicularly inside the magnetic field, then B is equal to F over 1 into 1 into 1, then the B and F both will be equal. So this is the definition of B. So we will write magnetic flux density B is the magnetic force or equal to magnetic force experienced per unit length conductor carrying unit ampere current and placed perpendicularly inside the magnetic field. So this is the definition of magnetic flux density B. Magnetic flux density B is the magnetic force experienced per unit length conductor carrying unit ampere current and placed perpendicularly inside the magnetic field. Now suppose the statement is magnetic flux density will be 1 Tesla if 1 Newton force is experienced per unit length conductor carrying unit ampere current and placed perpendicularly inside the magnetic field. Then this will be the definition for Tesla. So this is very important equation. It is used for the definition of the magnetic flux density B and also for the Tesla, right? This formula is used when a current carrying wire is placed inside the magnetic field. But the question is, if the magnetic field is uniform and it is into the page, into the board, into the plane of the paper uniform, and instead of the wire, any positive charge entering the field with velocity v and perpendicularly, then the direction of the force due to the Fleming left-hand rule is upward. Then this formula will be different. So instead of BIL sine theta, we will make some changes. B and I is equal to Q divided by T into L and sine theta. Look, this L, if taken this horizontal length of the field, then horizontal length divided by time is the horizontal velocity. So this is the horizontal velocity. So F is equal to BQL divided by T sine theta can be written as BQV sine theta. So this is the shape of the formula when charged particle entering the magnetic field. Now, due to this force, upward magnetic force, this charged particle bends up, and this is its direction of the motion. And after the field, it goes straight. Now the question is, at this point A and this point B, draw the direction of the force according to Fleming left-hand rule. This is the direction of the force. This is the direction of the force. So look, all forces are going to meet at a single point. So this part of the motion is circular because the force is perpendicular to the path of the moving charge particle. When the direction of the force is perpendicular to the direction of the motion, that is called circular motion. It means when the charge particle enters the magnetic field, it experiences force. It follows the circular motion. So in short, we can write magnetic force experienced by the moving charge particle is converted into centripetal force. So the path of the moving charge particle inside the magnetic field is not just curved, it is exactly circular path. But in electric field, it is parabolic, just curved path. So in magnetic field, it is circular, centripetal force. So the magnetic force is converted into centripetal force. Now the magnetic force is BQV sine theta, and the centripetal force is mv square over r. Now v velocity, one cancel, one remaining. So BQ sine theta is equal to mv over r. If the angle is 90, then BQR sine theta mv, and mass into velocity is the momentum. So the first formula, momentum of the charged particle, is BQR sine theta. When theta 90 degree, then we can write momentum BQR. So where P is the momentum, the product of mass and velocity. Now next, we can write M times V is equal to BQR, then V divided by RB is equal to Q divided by M, And this ratio, charge to mass ratio, is called specific charge. And it is measured in coulomb per kg. With the help of this specific charge, any unknown charge particle can be identified, which is also called charge to mass ratio. So the charge to mass ratio of any charged particle is fixed. For example, alpha, its charge will remain 2e, its mass will remain 4u. So this is constant for every charged particle, but it varies charge to charge. Alpha particles, constant. Beta particle, different but constant. Okay. Proton, constant but different from the alpha. Okay. For the different particles, different, but for the same charge particle, it will remain same. So the charge to mass ratio is V over RB. So it can be E by M for the electron, because the charge of the electron is E. It can be E by M for the proton. So E by M, charge to mass ratio, V divided by RB. Charge to mass ratio. V is the velocity with which it enters. R is the radius of the circular path. And B is the magnetic field, right, strength, which is provided to it. Yes.